tarde a todos. Bem-vindos aí à edição de setembro do Colóquio do IMECC. Com grande satisfação que a gente recebe a professora Helena Lopes, da UFRJ, que já foi nossa colega aqui no IMECC durante 20 anos, uns tempos atrás, e atualmente é professora lá na UFRJ. Então, a Helena começa a carreira dela fazendo doutorado em Berkeley, concluída em 1991. Depois ficou um período aí na Universidade de Kentucky, também nos Estados Unidos, e veio para a Unicamp em 92. Assumiu como professora aqui em 92, ficou até 2012, né? Então 20 anos como nossa colega aqui no IMECC. E nesse ano, né, 2012, ela foi para a UFRJ e assumiu a posição de professora titular lá na UFRJ. Nesse meio do caminho, né, nesse período, teve passagens por várias universidades dos Estados Unidos, Indiana, Penn State, Brown, também a Universidade de Cambridge, no Reino Unido. Titular, né, membro titular da ABC, da Academia Brasileira de Ciências, desde 2019, né, e da TUAS, que eu agora já não sei mais qual é o nome, The World Academy of Science, né, o nome politicamente correto aí do século XXI, desde 2022. E presidente do SIMPA a partir desse ano, né? Assumiu a presidência do SIMPA esse ano por um mandato de 4 anos até 2029. Já fez uma bela apresentação aí sobre o SIMPA ontem, no contexto aí do congresso da TIAN também. Foi palestrante do ICM em 2018, editora de vários periódicos, né? Entre os quais eu destaco o Órbita Matemática, que é o periódico da UMALCA, né? Que também teve o evento essa semana, né? A professora Helena é a Managing Editor do Órbita Matemática, né? Que é um outro episódio, um outro periódico que eu também encorajo todo mundo a considerar publicar no periódico da UMAL. Ela atua em equações diferenciais parciais, né? Especialmente dinâmica de fluidos, desigualdade variacionais, leis de conservação. Tem mais de 60 artigos publicados em periódicos de ponta, como Communications Mathematical Physics, Science Mathematical Analysis, Transactions of the American Mathematical Society, entre outros, né? E orientou 9 alunos de doutorado, 6 pós-doutorandos, entre eles 2 que estão aqui na frente, né? A Anne, nossas colegas aqui, a Anne e a Gabriela, né? Então, realmente, com grande satisfação ter novamente a professora Helena aqui apresentando o seu trabalho aqui no IMECC. Helena, por favor.
I'm going to switch to English. I think. Okay, so first of all, thank you very much, Marcus, for the very generous introduction and for the invitation to come and give this talk to you. It's a real pleasure to be back in Campinas. All right, so I'm going to be talking, the title of my talk is Beyond the Resolution of the Onsager Conjecture. So I'm going to start telling you a little bit about turbulence. Then I will tell you about what is the Onsager Conjecture. I'll tell you a little bit about Onsager. I'll tell you about what we know about the Onsager Conjecture. It's been officially settled, in fact. And then I'm going to tell you a little bit about work beyond the Onsager Conjecture, in particular my work. Okay, so what is turbulence? Turbulence is what we observe in turbulent flows. Duh. Okay, apparently disorganized flows for which the only plausible description is a statistical description. In turbulent flows, all of the quantities do not depend deterministically on the flow parameters. And a very important characteristic of turbulent flows is the sustained presence of small scales. Okay, so the best way to understand turbulence is some examples. Okay, so this is the picture that's in a book, an album of fluid motion by Milton Van Dyke. This is a beautiful book with a bunch of, it's a picture book, it's beautiful, and anybody interested in fluids should consult it because it's really amazing. So this is the wake of a tanker, okay, and what you see here in this wake are a bunch of squiggles and really, really small scales. Okay, here's another picture. This is the turbulent wake of a water jet. So what you do is you inject dye into a stream, and this forms. Okay, so you check it very fast, and then this picture forms, again from Van Dyke's An Album of Fluid Motion. This picture is from the fluids galleries, the wing of a tip vortex from an airplane wing. It's also turbulent. It's a little bit different from the previous slides, but you also have the presence of really, really small scale that you see better up here and on the edges here, along the edges. Okay, incompressible fluid flow is described by a set of partial differential equations, and a very important characteristic is the so-called Reynolds number. It's a non-dimensional constant which expresses the ratio between inertial and viscous forces. This is the formal definition. The Reynolds number is U times L over mu, where U is a typical velocity speed, typical characteristic speed of the flow, L is a characteristic length, and mu is the kinematic viscosity. So what I mean by typical length is, are we talking about kilometers? Are we talking about flow in a petri dish? Okay, so it's millimeters. What kind of scale are we talking about in the flow? That's what this L means. And U again means, are we talking about 100 kilometers per hour, 100,000 kilometers per hour? What are we talking about here? Okay, turbulence is an asymptotic phenomena which is related to high Reynolds number flows. Okay, so it's asymptotics here. That's what we're talking about. All right, so here are the set of partial differential equations which model incompressible viscous fluid flow. There's this little system. It looks like a 2x2 two-equation system, but actually the first equation is shorthand for three equations, one for each of the components of U. U is the velocity at time t and position x in the domain where the fluid is living. Okay, so you have the partial derivative with respect to time of each of the components of U, plus this weird operator, which I will tell you about in a minute, U dot grad, applied to each of the components of U. This is balanced by minus the gradient of pressure, plus 1 over Reynolds number, Laplacian of U, plus F. So F is an external force, and 1 over Reynolds number times Laplacian of U measures viscous forces. This measures internal friction of the particles of fluid. And then this is coupled to divergence of U equals 0, which is incompressibility. Okay, so the first equation, or the first set of equations, is just Newton's second law of motion. Okay? So U is U1, U2, U3 is the flow velocity, P is the pressure, and this weird operator U dot grad U means this. So it's really Uj ddxj summed in J applied to each of the components of U. So the operator U dot grad is just the sum of Uj ddxj. And F is a given external force. The mathematical viscosity of the flow is defined to be 1 over the Reynolds number. So Reynolds number going to infinity means viscosity is going to 0. The case Reynolds number equals infinity, or viscosity equals to 0, is known as the incompressible Euler equations. It's a set of equations. It was only the second PDE ever written. The first one was the wave equation by D'Alembert. The second was this Euler equation written by Euler in 1757. Yes, not 52, 57, 52. There was a mistake. Okay, so this is a description of the motion of ideal or inviscid fluids, and it's just the Navier-Stokes equation setting the Reynolds number to infinity. Okay, Euler and Navier-Stokes, as far as like a PDE problem, they need initial conditions, U at time t equals 0, which we will denote by U naught. And they need boundary conditions if your fluid lives in a domain with a boundary, such as a coffee cup, for instance. Okay? In this talk, we're going to assume that our domain does not have any boundaries, so it's either full space or the torus, periodic flow. Okay, so now I'm going to do a little calculation here, which sets the tone for the whole talk, which is energy balance. Energy, so I forgot to mention this, but the density is 1. So in fact, it's normalized to be 1. So in fact, the first equation, ddt of U, is really ddt of rho U. It's the momentum variation equation. Okay, so the energy is just going to be 1/2. The kinetic energy is just 1/2 of rho times U squared. Okay. So what we do to get this energy balance is we multiply the Navier-Stokes equations with u. In other words, take the inner product, and then use a divergence-free condition to write the following. We integrate this in space, and we rewrite this as the time derivative of 1/2 of the integral of u squared, which is just the time derivative of the kinetic energy. And that's equal to whatever happens when I multiply this by u. It's minus u dot grad u minus u dot grad p plus nu u dot Laplacian u plus u dot f. And then you can rewrite first terms as exact derivatives using the divergence-free condition. And so if you don't have any boundaries, then the first integrals are just 0, and the last integral is minus nu times the gradient of u squared. And then you still have the work done by the force F, the integral of u dot f. If you're in the inviscid case and you have no external force is like gravity or something, then this means that the kinetic energy is conserved. Okay? It's conserved as long as I can make sense of all of these calculations that I just did. In other words, it's conserved for smooth flows, or for sufficiently smooth flows. Okay, so we already saw that in turbulence, we get a bunch of squiggles. We don't expect the velocity to be smooth. Okay, so I'm going to define two important concepts here. One is called anomalous dissipation. The other one is called inviscid dissipation. Anomalous dissipation is a cornerstone of turbulence theory. It's also known as the zeroth law of turbulence in K41. K41 is the 1941 Kolmogorov theory of turbulence, and it's the benchmark. It's basically it's the basic theory for turbulence that we have to date. Everything else has been just tweaks of K41. Inviscid dissipation is related to anomalous dissipation, and it's something that applies to inviscid fluid flows. It means simply that the inviscid fluid flow does not satisfy the energy balance. So you're not smooth enough to make sense of the calculations that I just showed you. Okay? I will get back to what's anomalous dissipation in the next slides. But in any case, turbulence requires anomalous dissipation through the K41, and that requires non-smooth flows. So in 1949, Lars Onsager proposed the following conjecture: that inviscid dissipation might occur if the flow was less than a third regular, whereas if the inviscid flow is more than a third regular, they conserve energy. So the threshold was 1/3 regularity. Okay, I will get into what is 1/3 regularity in a minute. And research on the Onsager conjecture developed along two different fronts, one which is called flexibility, and the other one which is called rigidity. Flexibility, it means trying to find irregular solutions that don't conserve energy. Right? And this led to the construction of so-called wild solutions through the method of convex integration. All of these buzzwords you will learn about in this talk. Rigidity means trying to establish a regularity threshold above which the flow necessarily does conserve kinetic energy. Okay, so let me tell you a little bit more about anomalous dissipation. So here's K41 theory après Uriel Frisch. Uriel Frisch is a mathematician / physicist, I'm not sure. I think he considers himself a mathematician, working in Nice. He's pretty old by now, he's over 80. And he wrote a beautiful book called Turbulence Theory, in which he summarized it's basically a book on K41 theory. Okay, and he mentions the tweaks also. So K41 is the Kolmogorov theory of homogeneous isotropic turbulence. And I will mention so turbulence theory is a phenomenological theory. Okay, it's not something that's deduced from first principles. It's not something that's deduced from Navier-Stokes equations, and that's a huge problem. Okay, that's why turbulence theory is still a very active field of research. Because we really don't understand it. It's phenomenological. You observe things and you make some hypotheses. Okay, you make some axioms of turbulence theory, and then you prove theorems starting from these hypotheses. Okay, so two of the main hypotheses of turbulence theory are scale invariance. So the turbulent flow is assumed to be self-similar. In other words, there is a power h such that the velocity increments scale like lambda to a power h, to this power h. And finite energy dissipation in the vanishing viscosity limit. This is anomalous dissipation. A turbulent flow will have a finite, non-zero kinetic energy dissipation rate per unit mass. Okay? Now, if you remember, I have time to go back to the, yes. Okay. So here what we showed is that the time derivative of the energy is minus viscosity times the integral of the gradient of u squared plus the work, integral of u dot f. In the absence of a force F, okay, if you just throw away the external force, then the time derivative of the energy is minus nu times the integral of the gradient of u squared. Okay? And if nu is 0, or if nu vanishes, one would hope that this object here tends to 0, so that the kinetic energy of the limit flow is constant. Okay. So hypothesis 3 says that in turbulent flows this does not happen. Okay. You have a finite, non-zero limit as viscosity vanishes. So this is what's called anomalous dissipation. Oops. I didn't write that here, I should have. This is what's called anomalous dissipation. And it relates to vanishing viscosity limits. So the big difference is that inviscid dissipation relates to inviscid flows. Anomalous dissipation relates to vanishing viscosity limits. Okay. As I said in my first slide, a turbulence is an asymptotic theory related to Reynolds number going to infinity. Okay. K41 plus a scaling argument plus dimensional analysis gives us, this is a theorem, that the scaling exponent has to be 1/3. So the velocity increments have to scale like a power to 1/3, like the 1/3 power. And this is roughly equivalent to something called Holder continuity, that the velocity should be Holder continuous with the exponent 1/3. Okay? This is the hallmark hypothesis on scaling for turbulent flows. So the natural question is a third regularity plus Navier-Stokes enough to allow for anomalous dissipation? What is the regularity threshold, which implies energy conservation for the inviscid flows? And I'm throwing force here, always. So the Onsager conjecture can be restated as saying that the inviscid fluid flows with velocity which is Holder continuous with any exponent greater than 1/3 conserve energy. And if the exponent is less than 1/3, then it should be possible to find flows which satisfy inviscid dissipation. Okay, that is another reading of the Onsager conjecture from 1949, and this has been settled. Recently, it's 2018. I think the theorem is from 2018 and the publication is 2019, something like that. Okay. This is Lars Onsager. He was not a mathematician. He was a chemist. He was originally Norwegian, and then he immigrated to the United States. He was a chemist, and he also dabbled in physics. And he won the Nobel Prize in Chemistry in 1968. However, he wrote influential papers not only in chemistry, but in physics and in fluid dynamics, and in particular in turbulence theory. This is the first page of the famous 1949 paper where he proposes this conjecture. It's called Statistical Hydrodynamics, published in Nuovo Cimento. And this is the last page of the paper. Okay, so if we look at the last paragraph, he writes, in principle, turbulent dissipation as described could take place just as readily without the final assistance of viscosity. In the absence of viscosity, the standard proof of energy conservation does not apply because the velocity field does not remain differential. In fact, it is possible to show that the velocity field in such ideal turbulence cannot obey any Lipschitz condition of the form velocity increments bounded by spatial increment to a power n for any n greater than 1/3. Otherwise, the energy is conserved. That is now known as the Onsager conjecture. Okay, his argument in this paper is basically dimensional analysis. The term u dotted with u dot grad u must be bounded. Okay? He argues that it has to be bounded. And if you look at the dimensions here, you have basically u times the gradient of u, which is just u over length. So that's u cubed over L. So u cubed over L has to be bounded, which means u has to be c 1/3. That is Onsager's argument. As I said, he wasn't really a mathematician. Okay, let me tell you what happened on the flexibility side. So the flexibility side is trying to construct inviscid fluid flows which do not conserve energy. Okay, so the first paper after Onsager's conjecture is due to Vladimir Scheffer from 1993, and it was followed by a paper by Sasha Schnurman from 1995, and then a paper by Camilo Delelis and Laszlo Ziklihidi from 2009. Scheffer's 93 paper was unreadable. Nobody could read it. Okay, so Schnurman came and said, okay, let me try to understand this, and he produced a new version of the same theorem, but it's physically inspired, and therefore we can actually understand it. And then Camilo and Laszlo did a breakthrough, because the first paper by Scheffer and Schnurman, the first theorem, was non-uniqueness compactly supported in space and time, and therefore time-dependent energy. In other words, what they produced was a flow. Think about a glass of water, okay, that you put on your bedstand, okay, next to when you go to sleep at night. The water is nice and stopped and flat. The top of the water is just flat. You wake up in the middle of the night, you look at your glass of water, and it's bubbling. Okay, the top is moving, the surface is moving like crazy, and you go, oh my God, I'm having a nightmare. Let me go back to sleep. Okay, and then you wake up the next morning, and the water, the surface is nice and still again. Okay, so that is basically the gist of what they are proving. It's a velocity field, which is, when we say compactly supported in space and time, that means up until a certain time the flow is zero, completely zero, so the water is stopped. Okay, then it starts moving, and then it stops again at a future time. Okay. Scheffer and Schnurman's result was, this is technical, L infinity L2 in space and time, whereas Ziklihidi was L infinity in space and time, which is the correct physical space, the energy space. Okay, now what distinguished Camilo and Laszlo's work was the introduction of the method of convex integration in fluid dynamics. Okay. Then there was a series of papers after 2009. I mentioned here, I said 2013, Tristan, Camilo, and Laszlo, 2015, Tristan, Camilo, and Laszlo, 2016. There are many more. Actually, the period between 2009 and 2018, which was when Phil Izet basically cemented and said, okay, here it is, this is the Auditório conjecture, okay. That period was a very, very active period in this field, and basically every 2 months you had a new preprint with a new result. Okay? It got to the point that we were scared to open archive. In 2018, Phil Izet proved that there exist flows which are Holder continuous, 1/3 minus epsilon. So for every positive epsilon, there exists a flow, an inviscid fluid flow, which is C0, 1/3 minus epsilon, and compactly supported in time. Okay? It's periodic in space and compactly supported in time. That settles the Auditório conjecture. Okay, then in 2019, Tristan and Laszlo and Vlad proved the same result, but with a prescribed energy profile. So I give you an energy profile, any energy profile, and there exists a weak solution of the order equations, or if you want, an inviscid flow with that energy as a profile. In 2019, Tristan and Vlad did another breakthrough that they extended this to Navier-Stokes, and that was really unexpected. Okay, that there exists viscous flows with any prescribed energy profile, and there exists an inviscid limit with anomalous dissipation. this was a major breakthrough. However, there is a technical problem with their work, which is the notion that they have of weak solution of Navier-Stokes is extremely weak. It's not the standard notion that fluid dynamicists all know and love. In other words, it's not Leray-Hopf. Their work was a strictly 3D construction, did not apply to 2D. Then there was a series of other works, Colóquio 2021, and then a new paper that came out in 2021 where these people, Dallas Albritton and Guy Brue and Maria Colombo, proved non-uniqueness of Leray-Hopf solutions of Navier-Stokes with rough forcing. So the forcing has to be very rough, so we still don't know non-uniqueness with no forcing. Okay, that is a fundamental question in fluid dynamics. That we don't know yet, but with rough forcing we already do. Okay, also it's very interesting that this is not a convex integration construction. It's based on instability. Okay, since 2021, what else has happened? Okay, many more results using convex integration. Very recently, last year, we had a 2D result, and I mentioned that Phil's result is strictly 3 dimensions. In other words, the velocity has 3 components. 2D means that the flow is planar, means basically a symmetry with respect to the direction perpendicular to a plane. Okay, so the main issue, as you will see also in this talk, is that 3D has a lot more space than 2D, so things are easier somehow. Okay, so in the 2D version of IZET's result came out only last year by Vikram Giri and Rud. It's not that interesting. Okay. Last year we had non-unique. This is a big deal. Non-uniqueness in 2 dimensions for Euler with LP vorticity. I'm going to get into that in a minute. And this year, Sheskinov and Dai got an even better result of non-uniqueness with LP vorticity. Very, very unexpected. And then we have Albrecht and Colombo and Mescolini this year proved non-uniqueness for vanishing viscosity solutions of 2D Euler with LP vorticity. This is totally unexpected. Okay. All right. Let me go back to convex integration. How does this work? So in the earlier results, you substitute the Euler equations by something called differential inclusions. You start with a subsolution, and then you start adding ad hoc oscillations to your subsolution, small amplitude, large frequency, to push these solutions towards the boundary of a convex hull. That's the way you used to do it. Nowadays, it's a little more sophisticated. So, but again, you have it involves adding a high frequency oscillations here. So you rewrite your equation with this error term here, which is called the Reynolds stress term, and then it's supposed to have small amplitude, large frequency, and supported on these large frequency parts. Okay, then you construct perturbations using supported on these frequencies, which cancel this error term, and you end up and then you take Q larger and larger. You take a limit, and you get the solution. Okay, you have to choose these perturbations very carefully. The earlier works were choosing something called the Beltrami flows, and then which are special stationary solutions of the Euler equations in 3 dimensions, and then eventually people found these Mikado flows, which are they have everything to do with this children's game called Mikado, more sophisticated, and then you take the limit when Q goes to infinity, and that yields a solution by convex integration. Convex integration is a method to prove non-uniqueness, to prove weird solutions, to prove existence of weird solutions, to construct existence of weird solutions. The basic idea came from geometry, from the Nash-Kuiper theorem, where they prove that the unit sphere in Rn can be isometrically embedded in a ball of size arbitrarily small. Okay, basically, you can crumple a ball as small as you want, and that through a C1 embedded. And C1 is important. Flexibility is allowed by being C1. If you try to do it C2, you can't do it. Okay, so it's a similar work, but in this case, it's applied to fluid dynamics. The application is not trivial. Okay, so as I said, it's a novelty when applied to fluid dynamics, and I'm going to illustrate its use looking at some elementary problems. So let's think about problem 1. Okay, let me take a bounded open interval and try to find a bounded function whose derivative is 0 and which is supported, the absolute value of this function is just the characteristic function of my bounded interval. Okay. Of course, this is not possible, does not have a solution, because if the function has a derivative which is 0, then it's going to be constant. But since J is a bounded non-empty open interval, then the absolute value of f has to be equal to c, which cannot be the characteristic function of this small interval. So this is impossible. Now let's think about the same problem in 2 dimensions. So consider a domain in R2, which is an open disk centered at the origin, and try to find a bounded vector field U whose divergence is 0. That's substituting my f prime equals 0. Now I'm going to look at the divergence. Is 0 and U, the norm of U, the Euclidean norm of U, is the characteristic function of my disk. So U is supposed to be 0 outside of the disk, and its norm is equal to 1 on the disk. There are infinitely many solutions to this problem, and you can construct them explicitly. Here is a solution. You just take x perp over norm x times the characteristic function of x. That satisfies its divergence free, and its norm is equal to characteristic of d. All right, and then you can find other solutions very easily. Then you try to look in 3D. And in 3D, you need convex integration. Okay? So if you look at divergence u equals 0, u equals the characteristic of some given open bounded set, okay, then the theorem is that there are infinitely many solutions to this, and the construction is by convex integration. I will show you a construction of one solution to show that you have infinitely many. You require a bare category theory. Okay, so you have 3 steps. The first step is called the functional setup. So we introduce this function space x0, which are the smooth, compactly supported vector fields on my set omega. So they're all supported on omega and 0 elsewhere. And they're smooth, divergence free, and their norm is less than 1, strictly less than 1. This is called a set of sub-solutions to my problem. And then I'm going to close this with respect to the weak L2 norm, weak topology of the Hilbert space L2. L2 is just these square integral functions on omega. So the first step involves reformulating my problem. I'm going to set up this functional IA of u is integral of 1 minus u squared on A. And what I want is that I omega is 0 implies u is a solution of problem 1. That's what I want. If u belongs to x, x is the closure of that x0, then I want to be able to say that if I omega of u is 0, then u is a solution. Now, indeed, if u belongs to x, then u can be reached by a weak limit of some vector fields which are in x0. In x0, the norm of ul is less than 1 for all of them, and they're all divergence free and they're all smooth. Okay. They're also all supported inside omega compactly, and therefore you can use this to show that their weak limit will be 0 almost everywhere outside of omega. So u will be indeed supported in omega. The fact that the divergence of ul is going to be 0 implies that divergence for the weak limit is 0 just by weak convergence, a linear thing. And the fact that ul is less than 1 in norm implies that the weak limit has a norm which is less than or equal to 1. So if this object here is 0 and u is the norm less than or equal to 1, then what I have inside here is a priori non-negative, and it's 0, so the integrand has to be 0. All right, so indeed we can reformulate the problem in this way. Step 2 is to start adding oscillations to move towards a solution, from a subsolution to a solution. So we show that for any element of my original x0, and for any compactly contained subdomain, I can find a sequence of C infinity compactly supported vector fields such that they, for sufficiently large k, they also belong to x0. They converge weakly to V, and their L2 norm grows. Okay. Step 3 is a recursive construction, and you use step 2 in the facts above to construct recursively a sequence which is then shown to converge to a solution of problem 3 as reformulated in step 1. Of course, I'm putting a lot of dirt under the carpet, but under the rug, but that's fine. Problem 3 is an elementary context where we apply convex integration. Now, doing this for Euler equations is much more difficult because Euler equations are nonlinear. And that is basically what Camilo and Laszlo did in their phenomenal pioneering paper from 2009. Okay, let me tell you a little bit now about rigidity, the other side of the Onsager conjecture, trying to find a regularity threshold and assuming that the force is 0. So the earliest paper is from 1975. Please note, Onsager is 1949. On the flexibility side, nothing happened until 1993. Then on the rigidity side, the first work was from 1975 due to Pierre-Louis Soulem and Uriel Frisch, the same Frisch that I mentioned of the book, the turbulence theory book. They proved that if by any chance you have an inviscid solution, an inviscid fluid flow, which is bounded in time and has 5/6 of a derivative, think of this as Holder regularity, okay? Holder regularity is 5/6. Then you have conservation of energy. Then basically the state of the art, almost state of the art, is due to first IMECC. It's independent work by Greg IMECC and Peter Constantin and Andries TT from 1994. And they proved that if the flow is bounded in time, and it's this weird space here, this is a Bazov space, B 1/3 plus epsilon 3 infinity, it's very close to being 1/3 regular, Holder regularity 1/3 plus epsilon. Then the flow also conserves kinetic energy. The state of the art is due to Alexei Sheskinov, Peter Konstantin, Susan Friedlander, and Roman Schmidtkoy. It's a paper from 2008 where they proved that if the flow is L3 in time, B 1/3 3C0, then you conserve energy. So this gives you a little bit of a flavor of how delicate the problem is. Okay, this is from 1994, and then you move all the way to 2008, and what you gain is you drop the epsilon and you substitute infinity by C0, which means basically the higher order frequencies tend to 0 in your wavelet expansion, your Littlewood-Paley expansion. Okay, all right. All of these results apply to 2D and 3D. And then you have a legitimately 2D result due to Duchamp and Robert from 2000, where they proved that if the initial vorticity is bounded in LP for some sufficiently large P, then you conserve energy. LP means P is power integrable. Okay, vorticity is the curl of the velocity. It measures infinitesimal rotation of my flow. And then you can extend this to P, you can go all the way to P equals 3/2, following Sheskinov, Konstantin, Friedlander, and Schmidtkoy, because the velocity is going to be L3 in time, W1 3/2, and this is in this weird space of theirs, this L3 in time, B 1/3 3C0. Okay, now, there's something close to, so Kolmogorov has turbulence theory for real flows, okay, the flows in the world, which are 3 dimensions, 3D flows. Kreisman did a similar theory, but applied only for 2-dimensional flows. So Kreisman's 2D turbulence theory postulates a forward entropy cascade, and this implies that that you expect a regularizing effect in 2D, which is not present in 3D. In other words, you start very irregular, but the evolution itself becomes more regular than you would expect. Okay. It suggested the existence of some kind of dynamical mechanism which would prevent anomalous dissipation in 2D flows, even for so-called supercritical flows. So I need to tell you about criticality here. Okay. So the energy flux, which is the crucial term, it's the integral u times u dot grad u. How does it scale? We've already seen this once. It scales like u times u over L. That's the term u dot grad u times u. And then you integrate in space, so you get length to power n, where n is the dimension of your space. It's 2 or 3. And then you get time because you integrate in time as well. So this is u cubed, L to the power n minus n, n minus 1, times t. So based on this observation, Ramon-Schmidtko introduced so-called Onsager critical spaces, and which are Banach spaces whose norm to the power 3 scales exactly like the energy flux. And let me give you some examples of Onsager critical spaces. In 3 dimensions, L3 in time, L9 over 2 in space, L3 in time, H5 over 6. These exponents, when you have an H5 over 6, that means a derivative. 5/6 of a derivative, or think about Holder regularity, so with exponent 5 over 6. In 2D, L3 in time, L6, L3 in time, W1 3/2. Whoa. And in any dimensions, L3 in time, W1 3rd 3, in space, L3 in time, B1 3rd 3, P. Okay, and then in these spaces, this is where conservation of energy has been proven, where rigidity has been proven. Okay? All right, now I'm going to specify to 2D flows. So 2D Euler equations are the same set of equations on the torus. So my U now is U1, U2. And I'm going to be looking at weak solutions for which the vorticity is pth power integrable for some p greater or equal to 1. Smooth vorticities, in the smooth case, these are transported by the flow U, okay, and therefore the LP bounds are just preserved by the evolution. Wild solutions, only very recently, at the end of last year, we had the first example where you can control integrability of vorticity. We thought that was not possible, in fact. Okay, and more recently, there's even better control in this new result by Alexei Sheskinov and Mimi Dai. Here's a definition, just so you know what I'm talking about. So since I'm talking about a partial differential equation, and I'm talking about irregular solutions, and I need to come up with some notion of weak solution, and this is a sort of a standard notion of weak solution. It's basically inspired on distributional solutions. It's not a distributional solution, but it's inspired on distributional solutions, and it basically means that you can integrate by parts. And existence of such weak solutions is known. Okay. So I'm going to give you a baseline result just so you can get a feeling for the difficulty here. Okay, so suppose you have a flow U, which is a weak solution of the Euler equations, such that the vorticity is bounded in time and L3/2 in space. Then U is conservative, or in other words, energy is constant. Moreover, the local energy balance law also holds in the sense of distributions. Okay, so this result is contained in Sheskinov et al. Result because of this thing. But I'm going to give you an elementary proof, quote proof. Let me give you the idea of the proof. What we do is we take the Euler equations and we mollify them. So this is a standard procedure in PDE where you just integrate against this smooth test function zeta with a certain rescaling of it, and it gives you that your U epsilons are now smooth, and they solve this equation. So you have ddt of U epsilon, U epsilon dot grad U epsilon is minus gradient pressure plus an error term, R epsilon. Okay. The error term is the commutator, and then you just multiply by U epsilon. Here you have your local version and what you want to show is that this term here, when epsilon goes to 0, that this term vanishes. So I want to show that the error term vanishes in the sense of distributions, and what I actually managed to show is that they converges to 0 strongly in the space bounded uniformly in time, L1 in space. Okay. All right, so the way this is done is through uses of something called the Sobolev embedding theorem and Sobolev inequalities. The key fact that makes this work is that this term, U times U dot grad times U, my trilinear term, is integrable. That's the key element of this proof. Okay? And its norm goes like U cubed times W1 3/2. So we are in one of those critical spaces. So P equals 3/2 is a critical result. Okay. Moreover, it's not only critical, but it gives us a sort of a wall against, it's not possible to improve this. The technique does not allow for any improvement of this. So because of this, we decided to look at not a general inviscid fluid flow, but special fluid flows which are obtained as vanishing viscosity limits. In other words, asymptotics when Reynolds number goes to infinity. So I'm going to look at weak solutions, which are weak limits of solutions of Navier-Stokes U with a viscosity nu, which is going to 0. Okay? And I ask that the initial data converges strongly in L2. A family of such Navier-Stokes solutions is going to be called a physical realization of my inviscid flow U. So for these kinds of solutions, we proved a theorem, we meaning Alexei Sheskinov, Milton Lopes-Filho, myself, and Roman Shvitkoy, back in 2016, which says such weak solutions conserve energy. And then I want to note that the case P, this is for any P greater than 1, and the case P less than 3/2 is supercritical. So this was basically the first supercritical result for Euler. Okay, the key steps of the proof are this. We first show that the dissipation term vanishes. And then after this, we use strong convergence in L2 of the physical realizations to prove that the limit of the L2 norm, the energy, this is the energy at time t minus the energy, the initial energy. This is equal to the limit of the vanishing viscosity limit of the energies minus the vanishing viscosity limit of the initial energies. This one converges to U naught by hypothesis, and this one converges to U because we're in this case P greater than 1. This implies, therefore, that the energy at time t minus the initial energy is 0. In other words, the energy is conserved. So the key thing here to get this was to show that dissipation vanishes. To show that dissipation vanishes, we needed to get a differential inequality for the integral of the square of the vorticity. This is called the entropy in fluid dynamics. Okay, and this it had to be a special differential inequality where you have a power here which is greater than 2. That was the key fact. Very surprisingly, vanishing dissipation is actually a consequence of strong convergence. And in 2021, these gentlemen here, Samuel Collins, Sid Mishra, and Carlos Perez-Pulido, proved that these two things are actually equivalent, that strong convergence is equivalent to vanishing dissipation, and in particular to U being conservative. Okay? So they established that strong convergence in L2 implies no anomalous dissipation, in other words, vanishing dissipation. And then strong convergence plus no anomalous dissipation implies, by our argument, no inviscid dissipation. Okay, with Milton, we then decided to look at the case where you force the flow. And the reason that we wanted to understand this was because forcing is one of the preferred mechanisms of generating small scales in inviscid fluid flow. In other words, transitioning to turbulence. Okay, so in order to understand the case of forced flows, we need to tweak the definition of physically realizable weak solutions. We just added a technical condition on the way the forcings have to converge. Namely, F nu has to converge to F weakly L1, L2. And then we proved the following theorem, which was published this year, but was finalized last year, which is the analog of the Haller, Mishra, Perez-Pulido result. This was obtained with Fabian Jin, Samuel Haller, and Milton and myself. Okay, and it basically says that if the forcing is sufficiently regular, namely L2 in time, L2 in space, so it's got to be square integrable in time and space, and you have to have strong convergence, then U is energy balanced if and only if U converges strongly. If and only if you have vanishing dissipation. Okay, very brief discussion of the proof. One of the implications is very similar to the case of vanishing force, The other side is the heart of the matter. Strong convergence implies energy balance, because that's where you really need to show first that strong convergence implies vanishing dissipation. And that was done using this key lemma, in fact, which we had to prove, this key lemma. If U is converges strongly, then you can find a superquadratic function upsilon, such that upsilon composed with this integral in time here is bounded by the polynstrophy. So this is the integral in time of the entropy. It's bounded by the integral in time of the polynstrophy. This lemma allowed us to get a similar kind of differential inequality, not for the entropy, but for the integral in time of the entropy. In other words, for the dissipation. Okay, so, and using this, we then showed it's very easy to see that this will then imply that you have vanishing dissipation. Okay. We then abandoned the idea of looking for inviscid dissipation with vorticities in LP for P equal 1. That's one of the cases that's left over. Okay, and we decided to concentrate on, so let's say we can't prove that the energy is conserved, but we can still maybe look at anomalous dissipation. So the question now is, suppose the initial vorticity is integral in the space, and it's a bounded measure intersecting h minus 1. This is a technical condition. It basically says that the initial velocity has finite kinetic energy. These spaces are not compact in h minus 1, and therefore you don't have a priori the strong convergence of the velocities. So we don't expect to have an energy balance, although we do not have any example to date, but instead we decided to investigate anomalous dissipation. It's still possible that miracles happen, but if we don't want to rely on a miracle, let's try for a different result. So we considered solutions of Navier-Stokes, whose initial data converges in L2, and we proved the following theorem. This is independent work by Luigi De Rosa and Jamin Park from last year, and also independent paper by Tarek El-Gindi, Milton, and myself, which was written up last year. Okay, so the assumptions are the initial data converges strongly. The vorticities are bounded in time and into L1, into the interval functions. We have some technical conditions on the forcings F, and then this blue condition here. It's a very weird condition. The supremum in viscosity, the supremum in time, the supremum in center Z of the integral on disks centered at Z of radius R of the absolute value of the vorticity. This has to vanish when R goes to 0. Of course, if this is an integrable function, and then these disks are converging to points, then you expect the integral to be 0. So the assumption here are all these supremums. They vanish uniformly in viscosity, time, and centers. Okay. What this is telling us is that our vorticities doesn't form atoms in the middle of our fluid domain. Then in that case, there's no anomalous dissipation. One of the big deals here is that these conditions, 1 through 5, and this blue condition, are exactly the state-of-the-art conditions for which you can prove existence of such a weak solution for Euler. Okay? So we now know that any weak solution for Euler, which is obtained by a vanishing viscosity limit in the class of allowed weak solutions for which we can prove existence, does not have anomalous dissipation. It's a pretty big deal. Okay, as I mentioned, under these assumptions, any weak limit is a physically realizable weak solution of 2D Euler with this initial data. Okay, in De Rosa and Park's work there, they did only the case of no forcing. So we added forcing, and we have a completely different proof, which is based on a new a priori estimate. And I'm going to tell you very, very briefly about this a priori estimate. I'm almost done. We start by observing something called Nash's inequality in 2D, which says that the square of the square of the L2 norm of a function is bounded by the square of the L1 norm of that function times the L2 norm squared of the gradient. If you remove all the squares, it's just the square of the L2 norm is bounded by the L1 norm of the function times the L2 norm of the gradient. And the key to proving our result is the following refinement, which we obtained in this paper with Tarek and Milton. Milton and I with Tarek. And it says that if you have a family of functions which is bounded in L1, which is each function individually is also in H1, in other words, has a full derivative in L2, and if you have this no Dirac condition, then you can find a function upsilon, which is C1, convex, increasing, and most importantly, superquadratic, such that when you compose with the square of f in L2, this is bounded by the gradient of f, L2 squared. So it's a superquadratic function of the entropy is bounded by the square of the pull entropy. Okay? And that is what allows us to get, oh, I removed that, okay. So this is what allowed us to get a kind of a differential inequality, and then go back to to the previous results, okay? Previous arguments. So corollary. If you have a sequence, now I'm not going to be talking about one single solution because I'm talking about anomalous dissipation, so I have to be talking about vanishing viscosity limits. So I'm going to think about a sequence of vorticities, omega naught nu, bounded in the space of bounded measures in h minus 1. In other words, the initial velocities have bounded kinetic energy, such that they're given by a bounded measure which is non-negative, plus possibly an L1 function, W0 nu, which is such that this sequence is uniformly integrable. It's a technical condition. Then there's no anomalous dissipation for U nu. And I would like to observe that these conditions here are exactly the best conditions that we have for existence of solution to 2D Euler. Not only this, but we actually, in our refinement of Nash's inequality, we actually construct this function upsilon in a very explicit manner. We have a formula for this function upsilon, which allows us to get a rate. So we have a rate of anomalous dissipation, which is the log of viscosity to the minus 1/4. Okay, we don't know if this is sharp. We don't expect it to be sharp. Okay, in conclusion, the Onsager scaling is not the last word on inviscid dissipation. There is indeed a dynamical mechanism to avoid inviscid dissipation in 2 dimensions. Okay, so we vindicate Krajina, okay? And the story seems very different in 3 dimensions. There's every indication that this does not happen in 3 dimensions. Again, as expected. Okay. I want to emphasize that in the case of LP, W1 in time, and W1P in space, P greater than 1, we obtain solutions to the Euler which are physically realizable and conserve energy, and therefore these solutions cannot be attained by these flexible methods, the methods that are aimed at exhibiting solutions which don't conserve energy. Okay. So we thought at the beginning that this could support some kind of selection criteria, which is not available for Euler, but it turns out that in the presence of rough forcing, Maria Colombo et al.'s result excludes this. Okay, so the plot thickens, as they say. Okay, the case P equals 1, inviscid dissipation, this is wide open. Okay, we don't have compactness in L2 of the velocity fields, and we have therefore no tools to work on this. Okay, there's no tools to use for this problem. It's not completely excluded. Miracles have happened before for Euler, but so far, no cigar. Okay? And I point out that there is a discrepancy between what is known for inviscid dissipation of LP norms of vorticity, for which we can take P equals 1. Okay. We decided we're working on a different problem, which is slightly less ambitious. In the case P equals 1, can a vanishing viscosity limit be attained by convex integration methods? So far, we don't know. The current results that we have obtained, that are available, are not obtained by convex integration. Cannot be obtained by convex integration. And lastly, I want to point out that vorticity transport, I didn't really write the equation, but vorticity satisfies the transport equation by this flow U. And vorticity transport is a very important physical mechanism in incompressible fluid flow that's completely ignored by wild solutions. They're far too irregular for vorticity transport to hold. For vorticity transport to hold, you need to have P greater than 4/3, and therefore it's not good. And non-uniqueness is so what's open is produce non-uniqueness of a physically realizable solution. In other words, something that's attained by vanishing viscosity with vorticity and LP for some P larger than 4/3. The current examples that are available, the work by Maria Colombo and I think it's Maria Ilya and Anush Kumar, and also the new work by Alexei Sheskirov and Mimi Dai, they have non-uniqueness in LP, but P very close to 1. P is greater than 1, but very close to 1. So nowhere near 4/3. Okay. Thank you. I'm done.
Are there any questions?
Thank you, Helena, for your talk at the same time in the Colóquio of IMECC and TM. So I'm completely out from this domain of research, so maybe my question could be very naive. Do you think that the artificial intelligence can help you in some sense in your big theoretical challenges?
Absolutely. Absolutely. In fact, this week there was a new paper that was posted in the archive by a group of 22 researchers or 22 collaborators. It's a collaboration between Courant Institute, Brown University, and Google DeepMind, where they are trying to prove singularity formation from smooth initial data for 3D Euler. So that is for 3D Euler and also for 3D Navier-Stokes. Okay, so they have a breakthrough. And that was obtained using AI methods.
More questions or comments for Helena?
I just want to point out 3D is the macho problem, okay? I mean, we only work on 2D. We're peanuts.
Helena, thank you for the great talk. The results you presented are on the torus. Could you say a few words when you have a boundary?
Okay, so for Navier-Stokes, no, we can't, because then you'd have to deal with boundary layers, and that's another another porcupine, another problem. Okay, so no, we cannot do anything with boundaries, all right? But then there's it's a whole other can of worms where you have results for vanishing viscosity with boundary.
Any more questions or comments? So thank you very much, Helena, for the presentation. Thanks everybody for showing up. Our next edition is October 24, if I'm not mistaken. We're going to have again, we're going to have Professor Luna Lomonono from IMPA in our next edition of the Colóquio. Thank you everyone. There's a coffee break.